that, well, I describe myself as a recovering physicist. I got my PhD on that subject back in the Paleolithic. But I've been writing about it since and just learning stuff. And this is some stuff I learned just recently, and I found it so enthralling I wanted to share it with you today. I'm going to tell you a story today. It's the story of this small, out-of-the-way planet called Earth, and how, against all odds, it managed to become a rich, flourishing home for life. It's a saga that the scientists themselves are only just beginning to work out. They know a lot, but there's a lot more they don't know. What they do know, though, tells us that this story has, to me, astonishing levels of drama and suspense, considering that the most highly evolved protagonist barely made it to being pond scum. It's also full of long passages where our Earth would have, that our ordinary everyday planet, what we see out here, would have looked utterly alien to us, beyond anything in a science fiction movie. That's why I chose this title, which also has a second meaning. I'm sure you'll recognize the dude on the right. And on the left, of course, we have a 5-year-old Drew Barrymore stealing every scene she's in. I like this image because E.T. is carrying the potted plant that he nursed back to health magically. And it reminds us of what E.T. was doing on Earth in the first place. He was a botanist on some sort of scientific expedition. That's how he got stranded. He got enthralled by the forest and wandered too far and couldn't get back to his spaceship in time for an emergency takeoff. What the movie never does explain, though, is why E.T.'s expedition came to Earth at all. I mean, they must have known about millions of other planets in our galaxy. They're a star-faring civilization, obviously. Why this one? Well, I like to think that they'd somehow gotten word that an advanced civilization was starting to emerge here, and they crossed tens of thousands of light years, however far it was, to check this out. But who knows? Maybe they were doing more of a Star Trek thing, just traveling around to explore strange new worlds at whatever state of development those worlds happen to be. And if that's the case, here's the question. What would they have found on Earth if they hadn't happened to land in 1982 just in time to star in the movie? What if they came down some random point in the planet's past? Now, to answer that question, which turns out to be a surprisingly interesting one, we have to adjust our perspective on time. Most of us think that 100 years is a very long time. And it is in human terms, even though a lot of us in this room have lived a fairly substantial fraction of that. But a century isn't even an eye blink compared to the age of the Earth, which is 4.54 billion years. And we can, in Q&A, you can ask about how we know that number. But that is a humanly incomprehensible amount of time. That's putting it mildly. So to make it a little easier, I'm going to do the Carl Sagan thing and compress it into a single year. Here's our cosmic calendar. The Earth was born, and we'll get back to that, up there in the upper left-hand corner in the first instance of January 1st. And here we are at the last possible instant before, the Times Square ball comes down and rings in the new year, the next new year. Okay? And that's okay. So, but to give you a sense of how much we're compressing time in order to get 4.54 billion years, she is the symbol for billion, into a single year, that's a compression factor of 4.54 billion. Let's imagine 1 second before that last midnight. That corresponds to about 145 years in real time, which puts us somewhere back in the Rutherford Hayes administration. So if ET's expedition had come down at any time before that final second of our cosmic year, they would have missed TV, kids' bikes, cold beer in cans, and electronic speak and spell toys. And Spielberg would have needed a major rewrite. Well, okay, he could have managed that. But if ET's expedition had come down any time before the final minute of our cosmic year, that's over 8,000 years in real time, they would have missed all written history and more. If they arrived before the final hour of our cosmic year, the final hour of December 31st, it would have been more than 500,000 years in real time, and they would have missed modern humans entirely, also the Neanderthals. If they'd known where to look, they might have found a few of our ancestors, Homo erectus. And if they'd missed the final day, okay, well, you get the idea. E.T. and his crew would have been somewhat more likely to find ancient creatures like mammoths, giant sloths, cave bears, saber-toothed cats, all the classics from the comic books. But only somewhat more likely. All those creatures belong to the age of mammals. And that started with the asteroid that killed the dinosaurs 66 million years ago. Now, looking at our cosmic calendar, what day would you say that was? I'll give you a hint. It was 4:39 in the afternoon. Okay, what day?
The 30th.
Pardon?
30th, would you say?
A little bit further back from that. It's the day after Christmas, December 26th. And that span from the asteroid to us is quite a bit less than 2% of the total age of the Earth. We think that's a long time. Compared to the age of the Earth, it is not. Now, E.T. might have had a little bit better luck seeing dinosaurs themselves because they lasted almost 4% of the Earth's lifetime. This is 200-something million years down there. And okay, 4% is a better chance than we're ever going to have, but still, it's pretty small in the grand scheme of things. So let's try again. Considering all the weird and wonderful fossils we've found, trilobites and, goodness, whatever else, crinoids, certainly E.T. would have found weird and wonderful plants and animals to study and so forth. And he might have, he just needed to come down sometime after the Cambrian explosion, it's called, which was 539 million years ago. What that means is when we first start to see plants and animals in the fossil record. Before that, nothing. It's the Burgess Shale, if you remember that book. Guesses for the date on that? November 18th, and the lead-in to Thanksgiving. That's just, so this green area is the only part where you can see actual fossils or living things. That's 12% of our cosmic year. So the odds of ET hitting a time when life forms were visible to at least to our naked eyes, who knows what he could see, but to our naked eyes was about like tossing 3 heads in a row. You know, it's not impossible, but that's not the way to bet. The odds are much, like 7 to 1 that he would come down, you know, encounter Earth sometime in that big pink area. I like to think ET would be just as fascinating. What he would know is that this was a world in the process of becoming. It was evolving towards a planet that was slowly evolving towards a planet that could support complex life. And there's a lot going on there. And that's, in fact, the story we're going to tell today. Let's fill in, and let's start by doing that by filling in that pink area a little bit more. Geologists divide Earth's history up into 4 eons, which are a bit like the planet's seasons. We've already met the most recent one. It's called the Phanerozoic, which is from the Greek words for visible life. And the geologic signature for when it started was when you first start to see multicellular creatures in the fossil record. The eon before that is called the Proterozoic, which is before life. And the geologic signal for its start was the first appearance of oxygen in our atmosphere. And in a minute, we're going to see what a big deal that was. Earlier than that, we have the Archean eon. That's from the Greek word for ancient, which is the same word where we get archaeology and archaic and a bunch of others. Geologists mark the start of that season somewhat arbitrarily by the oldest surviving rocks. They're up by the Great Slave Lake in Canada, and they're about 4 billion years old. A little over 4 billion. I got curious, by the way, and I've always heard that name, the Great Slave Lake. What? And I looked it up, and it doesn't mean what you think it means. That word slave is the English translation of a French corruption of a Cree word that means something like that other tribe over there. So anyway, 4 billion years. There are certainly rocks before that. It's just that they've been melted or eroded away by geologic processes, which brings us to the, I'm going to say the last, actually, it's the first eon, the Earth's infant years, and trust me, terrible twos doesn't begin to capture it. Anyone know what it's called? This is the official geologic name for it. The Hadean, Hades. And they mean that literally because the Earth was pretty much born in hell. And when I say the Earth got beaten into shape, I mean that literally. Let's go back to the very beginning of our cosmic year, the end of the Hadean. And what you're looking at there is the solar nebula. 4.54 billion years ago, that's when the clock starts, when this thing forms. It was basically a mass of interstellar gas and dust that had collapsed down into this flat, swirling disk a few billion miles across. It's roughly the proportions of a photograph record, if anybody remembers what those were. And when I say the swirl, I mean that literally too. It was, these outer parts are orbiting the center. This whole thing's held together by gravity. Now there's this whole story, I could do a whole lecture on how and why this thing formed, and why they're all over the galaxy. This is a very common phenomenon. But for now, we'll just have to accept that it did. And E.T. would have known about this like this all over the galaxy. It was common as dirt. But we're going to look at what was happening inside the disk. Now, 98% of it, virtually all of it, was hydrogen and helium, which are not only the most abundant elements in the universe, but the lightest, but the most abundant by far. And most of that hydrogen and helium fell into the middle. You can see that starting right here, and this mass of gas got so hot and dense that it ignited thermonuclear fusion, that it essentially became a continuous hydrogen bomb held together by gravity. And we still see this thing in the sky every day, called the sun. And at night we see zillions of others just like it in the stars. That's what we call them. Suns like ours. For our purposes, though, the real action is in that other 2%. Astronomers call this stuff dust. They can see it out in interstellar space. They're actually, their particles are more like smoke particles. But they contain, well, the most common elements the most abundant elements after hydrogen and helium: carbon, nitrogen, and oxygen. Now, most of them are in the form, they're in chemical combination with the most abundant element, hydrogen, which gives us methane, natural gas, ammonia, and of course, water. And because it's cold in space, these things are solid ices. So you can imagine you got these little grains of ice and stuff floating around out there. There's also some of the grains had rocket silicates and carbonates, usually with things like calcium and magnesium combined. There's a bunch of iron, with grains of iron, and traces of just about everything else, up to and including uranium. But now, over tens of millions of years, though, because this thing has condensed, these grains start to collide and stick together, electrostatically at first, but then eventually they start to aggregate into grit, and then pebbles, and then rocks and boulders. And eventually they get so big that gravity takes over. And they start attracting each other by gravity, at which point they don't just stick together, they slam together. Our early solar system, well, this is a bit melodramatic, but you get the idea. These rocks were just smashing into each other, and the bigger ones grew faster than the small ones. Eventually you got protoplanets, among them Earth. And if ET had stopped by at that point, Earth would have looked something like this. If you're a Star Wars fan, it's a bit like the lava planet Mustafar. But regardless, it's basically a ball of molten rock and iron covered with a thin crust where it's cooled on the outside. However, and that's what the Earth probably would have looked like about 100 million years after, about a week after, in our cosmic year, after the formation, about 100 million years. Okay, so what's missing? Okay, here's the Earth. What's missing from the Earth?
H2O.
Pardon?
Water.
Yeah, well, that's one.
Land, like anything?
Here's the clue. The bombardment hadn't stopped. There were still things slamming in here. And that wouldn't taper off for another 600 million years, and it's never really stopped. Okay, well, here's...
Question.
Yeah?
Would it be a core?
Yes, actually the iron, because it's heaviest, is falling in.
Okay, you said what was missing. What was missing was your question, correct?
Yeah, what was missing? Yeah.
So I said a core, because everything's slamming together. So you're saying
Well,
that's
there's a
not
core.
true.
There is a core to this
There is
theory.
a core. Okay.
Yeah, right, yeah. This is iron and rock here.
What about protection from solar wind?
The solar wind is blasting away at this thing. It's not protected from the solar wind.
The atmosphere's clear.
Right. Anyway, so here is a NASA simulation of what scientists are pretty sure happened around this time. And this simulation is sped up to compress the events of about 35 hours into just under a minute. But remember, when you look at the simulation, that this isn't just an animation. They calculated how every particle that you see is gravitationally attracting every other particle. So this is a calculation. Now see if I can actually get this to work. A Mars-sized body hits the Earth. Debris forms into two bodies. This is all by gravity. The smaller of the two becomes the moon. And that, folks, is how we got our moon. Again, for the Q&A, we can talk about how we know this happened. That Mars-sized body has actually been given its own name, also from the Greek. It's from Greek mythology, Thea, who was the mother of the moon goddess Selma. Okay, well, the Thea collision may have also given us a few other missing pieces, air and water. Or maybe not, but in any case, the key idea here is that the collision would have, well, turned the Earth back into a molten blob. If we had any oceans, it would have been vaporized. And then it recondensed, surrounded by this haze of vaporized rock, and that might have included, there was a lot of water and ammonia and methane and other stuff, light elements bound up in the rock, and this would have released it. The rock would have settled out pretty quickly. The calculations say 2,000 years, leaving the gases. Meanwhile, more gases would have come boiling out of the volcanoes, like water, ammonia here. Also, a few other delightful things like hydrogen sulfide and sulfuric acid. These gases would have remained surrounding the planet. Trust me, you couldn't breathe it. You would not want to breathe it. But the water, because water condenses at a pretty low temperature, it would have rained down to form the oceans and dissolved a lot of carbon dioxide too. That's what that diagram shows. So if E.T.'s expedition happened to visit a few hundred million years, after a few hundred million years of rainfall, around 4 billion years before the present, it would have seen something like this. This is an artist's conception, of course, but this is to show it's still hot on the inside. There's still a lot of lava. The oceans are collecting, and the craters, of which there are a lot because the bombardment was still going on. It's an exaggeration to say that a dinosaur killer was an ordinary Tuesday, but not much of an exaggeration. And eventually, we probably got to this. Kevin Costner's Waterworld, except even Kevin couldn't breathe that atmosphere. The water would have covered everything. Notice there are no continents there. The geologists still argue about when the first continent started to form, but it wasn't yet. If there was any dry land at all, it was probably hot spots like Hawaii or Iceland or something. Just a few isolated things. But the appearance of the oceans and an atmosphere to set the stage for the next chapter. Like microbes emerge and wreak havoc. And I'm not kidding about that either. Now, the origin of life is one of these mysteries that scientists are still scratching their heads over and arguing about. Endlessly, it's one of the biggest mysteries. But we do know a few things. One, because we've been able to examine living cells in enormous down to molecular level, we know that everything going on inside us is basically chemistry. It's incredibly complicated chemistry, but it's all natural processes. There's no magic spark that's required. Dr. Frankenstein to the contrary. So the origin of life must have been a chemical process. We know that. And second, the first living things, the first thing you could reasonably call living, must have looked a lot like today's bacteria, which is what these guys are. And why? Because it's hard to call a cell something living unless it has some way to reproduce, to metabolize food, to hold itself together with some kind of cell membrane. And modern bacteria do that in about the simplest way imaginable. Here's a diagram. It's in Cyrillic because this is an illustration from the Russian children's book. The Russians don't fool around with child education. Leave aside the eyes and the little hands. But this pretty much captures it. A bacterium, I mean, there's a lot going on in there, but it's got DNA and ribosomes and all of that, but it's basically a bag of parts, about as simple as you can get. The devil's in the details, though, because in the late 1970s, now I use the word bacteria for this, but that's not quite right. Biologists noticed that there were some single-celled organisms that looked like bacteria and acted like bacteria, and it always seemed to be bacteria, but they weren't bacteria. I mean, the DNA was the same, the ribosome, all that stuff, the metabolism, the cell machinery, but they had cell walls and internal chemistries that were profoundly different. So different that they actually represented a new, distinct domain of life. If you know Cyrillic, you'll know that doesn't say bacteria, it says archaea. There's that root word again, ancient. Old ones, and they were given the name. Here's a family tree of microbes. And there are the bacteria over there, and the archaea over here. And even though archaea means old one, ancient, the ancient ones, they're actually pretty much the same age. So far as we can tell from molecular evidence and genetic evidence, they emerged from Luca, the last universal common ancestor, at essentially the same time. So they're brothers. And it turns out that this difference is going to become important later. However, talking about time brings us to the next point. Even though we don't know how life began, we have a fairly good idea of when and even where. When. The oldest unequivocal fossil evidence for life are rocks like these from Australia on the left. If you look closely, you see there are layers in there. And we know how they were formed. They were mats of bacteria growing on rocks and depositing layer after layer after layer over the course of years, centuries. And we know that because you can still find very similar things growing today. These are living, they're called stromatolites. These are living ones from another part of Australia. They're not very common, but you can find them. However, this fossil stromatolite, is 3.5 billion years old, March 25th on our calendar. And it's the oldest unequivocal fossil evidence. I mean, that's life. So life must have began before that. Actually, a fairly long time, because it takes a while to evolve even a bacterium. But it must have happened after the oceans formed, which is 4 billion years, give or take. And there's actually a lot of indirect chemical evidence and such that, and genetic evidence, all of which points to 4 billion years. So we know, roughly give or take 100 billion years, we know that's about when life began. Which, by the way, is almost as soon as there was a liquid ocean, which means, was the origin of life easy? Inevitable? E.T. could have told us, maybe. Until we hear from him, what about the where? Well, the original idea in the old days was that the origin took place on the surface of the planet, somewhere on the rocks, or in Charles Darwin's phrase, in a warm little pond, where all the right chemicals can mix and maybe get a spark from lightning by the Frankenstein style. It would have looked something like that. And yes, it would have been that desolate. Remember, no plants, no animals. And E.T. might have looked carefully at ponds like this, but he probably wouldn't have found anything alive. Because the thing about the warm little pond is that the surface of our planet, if there was any surface, maybe little islands, was pretty risky. There's not much of it. Isolated, not protected from the ultraviolet. That goes to your question about solar wind, or the solar wind for that matter. And the sun was putting out more ultraviolet then than it is now. And that bombardment was still going on. So, anything out there could get blasted at any time. It's not a particularly favorable place. I mean, maybe, but besides which, there is a more likely place that was found only in the 1970s. And it's hydrothermal vents deep in the ocean. And hydrothermal vents are, where there's hot spot where there's lava close to the surface, and you get water seeping into the cracks in the rock and coming up, like a bunch of old faithfuls deep in the ocean under a few miles of water, just erupting up there at extremely high temperatures. The first time a scientist discovered one of these things, in the 70s, they tried to put a thermometer down one of these things, and the thermometer melted. They're hot. But the thing about these hydrothermal vents, well, they're protected from the bombardment, they're protected from the UV, and most importantly, they're a chemical wonderland. Life is a chemical process, remember? And just everything you can do, I'm sorry it's so small there, but everything, temperature gradients and dissolved minerals and methane and ammonia and hydrogen cyanide, which is a nice reactive stuff. They're also crystal surfaces, just condensing everywhere. And crystal surfaces do really well catalyzing reactions. Particularly iron pyrite, fool's gold, iron sulfide. And there's lots of it. So this seems like a much more likely place. E.T. probably would have taken a very close look. So the oldest organisms we think were probably clustered down here at the bottom of the ocean, clustered around these vents, what we now call extremophiles, because they liked extreme environments, not warm little ponds. So E.T. would have looked very closely there, but there's a problem though. Life evolved at the vents, but then it was stuck at the vents. I mean, they had to crowd around. It must have gotten a lot of competition. After a few 100 million years, there's not a lot of space left. And the problem with the vet fields is they come and go. They form and they die, and so you get left stranded and die out. So there was an opportunity for some entrepreneurial organisms, microbes, to go out and find another energy source. Not this really hot water, but something else. And up near the surface, they did find exactly such a source. It was diffuse, it was low energy, hard to gather, but it was everywhere and it was utterly reliable. So around 3.8 billion years ago, give or take, well, you know what I'm talking about, life went solar. But maybe it didn't go green, not yet. These bugs were doing photosynthesis, yes. And photosynthesis really means it's using the energy of the sun to turn carbon dioxide and hydrogen-bearing compounds into organic molecules. That's chemically what it means. It's just harnessing that energy of the sun. But it may not have been the kind of photosynthesis we're used to. It's hard to know for sure, but again, looking at chemical traces and genetic evidence, a lot of scientists think that the first photosynthesizing organisms captured light with a relatively simple molecule known as retinol. And it's called that because it's almost identical to the pigments in our eyes that allow us to see. And the thing about retinol is, there are still organisms around today that use retinol to do photosynthesis, so we have a fairly good idea of what these original ones must have looked like. Here's one example. It's called, and most definitely are not green. Here's one example. It's called haloarchaea, which means salt-loving old one. And it's purple. And here's a wider view. This is one of those salt evaporation ponds at the edge of San Francisco Bay. If you've flown into like San Jose or something, you've certainly seen these out the window of the plane. And so maybe the surface of the ocean back then looked kind of like that pond. And the upper layer of the ocean would have been full of these purple guys. So if ET had come around then, he would have found the Earth would have been purple for maybe a few 100 million years. You notice that the artist here, this is an artist rendition, not a photograph, but the artist has included a small landmass. That's no accident. There weren't any full-size continents yet. This is about 3.5 billion years ago. But the Earth was definitely accumulating patches of dry land, and ET would have made a beeline for the shorelines of one of these many continents, and he would have found something like this. Yes, it would have looked about that bleak, remember, no plants, no animals. The moon, yes, was a lot closer then than it is now. But he would have found these stromatolites growing in the shallows, with photosynthetic guys. And if you looked very closely, he would have found that, he might have found that the purple photosynthesizers had company. Microbes that could do photosynthesis with a light capturing molecule that could capture wavelengths that the retinol-based guys weren't using, that the purple guys weren't using. So that their light catching ability had to be the color complement of purple. What's the color complement of purple? It's green. I'm talking about chlorophyll. And in fact, the first chlorophyll using photosynthesizers probably looked a lot like these guys here. They're called cyanobacteria. They're still around. They're really big players in the pond scum game. I mean, here's some growing in a beaker.
Mitch,
Yeah?
does the prefix cyan, is that a Greek origin? Or
Yeah.
can you tell us?
It actually means cyan, which is not green, but they're kind of blue-green. But they are using chlorophyll. But as you can see, a lot of them are green. So there's some more. They're really big on the pond scum game. Now, these guys had to be really efficient because after all, they were competing with the purple guys, and they're just taking the leftover light that the purple guys weren't using. So the chlorophyll-based photosynthesis had to be incredibly efficient, and it is. It's quite complicated, really complicated. But it was very, very efficient. But there was such a thing as being too efficient. As these guys began to spread and take over, the thing about chlorophyll-based photosynthesis is it produced a waste product. And like a lot of industries, human industries, they just dump this waste product overboard, letting it foul their environment. I mean, they're bugs. What do they know? And so this stuff built up. And the thing is, this was a particularly nasty waste product. It would corrode or kill just about anything it touched. Guesses as to what it was?
Oxygen.
Pardon?
Oxygen.
You got it. Oxygen. Some of the nastiest, most reactive stuff around. Now, we think of oxygen as the stuff of life, and it is now. But microbes back then had no defenses against it. There were no antioxidant molecules inside them. They had to evolve. No advanced cellular repair, no tough membranes. So this nasty pollutant slowly built up until about 3 billion years ago, roughly May 4th in our cosmic year. It was just environmental havoc. We can't know for sure because microbes don't leave fossils worth mentioning. But it just must have killed them off, leaving a mass die-off. Probably the worst mass extinction in Earth's history. And on top of all that, while all this was happening, these are dead bacteria in an electron microscope. At the same time as all that was happening, the oceans began to rust, literally. What do I mean? Before there was oxygen dissolved in the water, there was a lot of dissolved iron compounds, soluble iron compounds. They were coming out of the black smokers or the hydrothermal vents. This is a schematic. But when the cyanobacteria, when the photosynthesizers started producing oxygen, Well, iron plus oxygen, what do you get? Rust. So you started getting deposits, they formed bands, but deposits of essentially rusted iron. And in fact, this stuff is all over the world. They were all deposited during this ocean busting period, about 3 billion to 2.5 billion years ago, May-June time frame in our cosmic year. It's the source of most of our iron ore today, almost all of it. We're still mining this stuff. It was actually first discovered up near Lake Superior in the iron mines up there. And then but this didn't stop. The cyanobacteria just kept pouring this stuff out. And when they proliferated to the point where the iron ions couldn't keep up, where the ocean couldn't keep up, well, the oxygen had to go someplace. Where's it going to go? It's called the Great Oxygenation Event. It went into the air. From about 2.4 to 2 billion years ago, June, July time frame in our cosmic year, over hundreds of millions of years, the oxygen content of the atmosphere went from nothing to maybe 10% of the present day oxygen. You still couldn't breathe it. That's worse than Mount Everest. But it was enough to start. By the way, this is when the Archean eon gives way to the Proterozoic. Remember I told you oxygenation. That's the symbol. Not only was it building up, but it was basically slowly burning up our protective greenhouse layer. And we think of the greenhouse effect as a bad thing today, and it does cause problems. But without an atmosphere, without a greenhouse effect, the Earth would be frozen solid. The sun's just not bright enough, and the sun was actually dimmer back then. So most of the atmosphere at this point was carbon dioxide. But there was also a fair amount of methane in there too. Methane, natural gas. And it's actually a problem today. Methane is a far more powerful, about 40 times more powerful at trapping the heat than carbon dioxide is. Carbon dioxide is actually a pretty lousy greenhouse gas. It's just that there's so much of it. Methane is really powerful. That's why we worry so much about methane leaks and so forth. Anyway, so there's a lot of it in the atmosphere, but as soon as you expose methane to oxygen, it fairly quickly, it's the same reaction that powers your gas furnace. It turns into carbon dioxide and water. The air didn't burn, but it was more slow, but it did that. And at the same time, we're finally getting continents showing up, and there was a lot of rock weathering, which is what happens when you get rainfall onto fresh rock, and the rock weathering has the effect of soaking up carbon dioxide out of the atmosphere, basically turning silicates into carbonates if you're interested in chemistry. So basically the greenhouse got weaker and weaker and weaker. And the sun, by the way, was dimmer then than it is now. Well, what happens? The northern ocean started to freeze. And as soon as you had all that ice pack up there, it's reflecting sunlight back into space instead of absorbing it. So that energy is just getting reflected back instead of being absorbed. And that means there's less energy to keep the water melted, so more ice appears. So things got colder, more ice, more reflection, and it became a vicious circle of runaway ice thing. So if ET had come by at about this time, that's what the Earth would have looked like. This was the first Snowball Earth, the Huronian glaciation for Lake Huron. For about 200 to 300 million years, there were at least 3 major ice ages where essentially the ice extended almost down to the equator. Probably not as far as in this picture, but pretty close. It's like, if you're a science fiction fan, it's like the ice planet Hoth and The Empire Strikes Back. Just ice everywhere. And the photosynthetic microbes, which need sunlight, well, they were able to survive only if there were a few open patches, maybe some volcanoes or whatever melted some areas. But it was touch and go. But they did manage to hang on until the snowball finally melted about 2 billion years ago, in the July time frame. Probably because new continents were forming and spewing CO2 into the air. And that, in turn, set the stage for a gigantic global yawn. It was a stretch of geologic blah that lasted 1 billion years, 1/4 of the Earth's history. More than 80 days on our cosmic calendar, long enough to take us from early August to Halloween. Geologists call it the boring billion. I'm not kidding, they do. And that's because geologically, at least, nothing really changed. They're not sure why, but the temperature stayed warm this whole time. The climate was steady and mostly ice-free. Actually kind of pleasant, aside from the fact you couldn't breathe. And there was nothing to eat but green slime. There were geologic things happening. There were continents that were moving and splitting and colliding the way continents do. There was something called the supercontinent Columbia became the supercontinent Rodinia, and a whole different story. But there's nothing dramatic, no dramatic upheavals. The oceans were stable, maybe even stagnant. And so geologically, Earth was in stasis. But biologically, though, it was anything but static. There was some serious stuff going on. Beneath the ocean, the Earth was undergoing its most profound change yet. And if ET had come along about 2 billion years ago and looked at a sample of seawater through a microscope or whatever he used, he would have found all the usual microbes, but also something new. Something that looks like it was right out of our biology textbooks, which I'm sure we all remember. These things, these guys were obviously related to the other microbes we've been talking about, the bacteria and archaea. They had the same DNA, the same metabolic processes and so forth. But they were about 10 times bigger, for starters. And more importantly, as you can see in this diagram, don't worry about the names and the details, but as you can see, they had reorganized and repackaged everything inside. Remember, bacteria and eukaryotes are more or less bags of parts. So instead of free-floating coils of DNA, they had packaged all that genetic material inside its own membrane, this guy right here, and formed what we now call the cell nucleus. But not just DNA, they had repackaged a whole bunch of other key functions and all kind of new structures. We got, Golgi body, whatever that is, the central endoplasmic reticulum. I love that word. All that stuff we memorized under duress in high school. And these guys even invented sex. I won't sure exactly when, but from a microbe point of view, sex is this ridiculously overcomplicated way of reshuffling genes during reproduction. So anyway, these cells had undergone this quantum leap in complexity and sophisticated. It's like going from an open plan office to a high-tech factory complex. And I can't overemphasize what a big deal this is in the history of life. It would take a while. In fact, it would take more than the boring billion. But eventually, these are the cells that would start coming together to form multicellular creatures like us. Or to put it another way, you, me, everyone here, the trees outside, the birds, the squirrels, the grass, everything, every living thing you have ever seen with your naked eye is descended from these guys. That was a whole new domain of life. They're called the eukaryotes, which is Greek for true nucleus.
Can you translate what the word actually means, the origin of the word, the etymology of the word eucalyptus?
I'm sorry?
Can you explain the etymology of eucalyptus?
Eukaryote?
Yes.
It's Greek for true nucleus.
True nucleus.
Yeah, right. And that's what the bacteria in archaea are called prokaryotes, which is before the nucleus. But yeah, true nucleus. And that's the profound importance of this development makes it all the more frustrating that we don't have the slightest idea of how or why and in what order all this repackaging happened. That's not fair. There are a lot of ideas, and biologists just argue endlessly, but nobody knows for sure. It may have had something to do with cells protecting themselves from all that oxygen, but beyond that, well, maybe E.T. could have told us more, but all we have right now are a few clues. So here's one clue. These things are colored green. They aren't actually green. These little green organelles, that's just for illustration purposes. Here's a close-up. And if we remember high school biology, these are called the mitochondria. They're the powerhouses of the cell. The key point here, don't worry about the details. The key point here is this looks a lot like a bacterium. These things actually have their own DNA. These small circles up here, they have their own ribosomes. They have cell walls that look like the cell walls of bacteria. And everything points to the idea that mitochondria are descended from once free-living bacteria that somehow took up residence inside some host cell. We'll get back to the host cell in a second. We don't know how that happened. Maybe the host tried to eat it and changed its mind. I mean, we don't know. This was called symbiosis. They worked together. And well, why? Why would the host cell bother with this? The genetic and chemical evidence points to the original mitochondrial bacterium, things that became mitochondria, may have belonged to the same family of microbes that cause things like typhus and Rocky Mountain spotted fever, delightful creatures. But they were certainly part of a group that had figured out a clever way to deal with oxygen. Oxygen driving everything. Namely, they figured out how to run photosynthesis in reverse. And this is the most technical slide I've got. Hopefully, I know. Look at it. Okay, well, let's just do that. Photosynthesis in reverse. let's just skip past this. They did. They used oxygen to do that. And that worked out so well that a few 100 million years later, pick a number, about 1.6 billion maybe, some of those eukaryotes started a symbiosis with cyanobacteria, and they got imported, and they became the chloroplast. And again, don't worry about the details, but chloroplasts also have their own DNA, they have their own ribosomes, and of course they've got the chlorophyll, which allows the host cell to do all sorts of wonderful things with sunlight. And speaking of the host cell, we've got a pretty good idea. There were archaeans. And a particular strain of archaea that was discovered only in the last 10 years or so. They're called the Asgard archaea because they were discovered, has nothing to do with Marvel Comics. They were discovered up in an area called Loki's Castle, which is a hydrothermal vent field between Norway and Greenland. And they turned out, Asgard archaea turned out to have all these compounds and structures that are found only in eukaryotes. So it's almost certain that they were the host cell. And here's our tree of life with a whole new branch. The third domain, eukaryotes. And the bacteria, archaea, and you notice the way this is drawn, eukaryotes are an offshoot of the archaea. Now, of course, the success of these guys, they were very complex. The success wasn't preordained. For most of the boring billion, it was kind of tough for them. There weren't many of them around. The oxygen levels had fallen again to maybe 1% of today's level. The oceans were stratified, all the oxygen up at the top. Most of the deep waters, they couldn't function. The eukaryotes couldn't function. There weren't a lot of nutrients. There were primitive, most of the photosynthesis was by cyanobacteria. They were out-competing eukaryotes, and a lot more prokaryotes in general. But towards the end of the boring billion, roughly 800 million years ago, the atmospheric oxygen levels started to surge again. We don't know why, but they went from about 1% to 100% of today's oxygen levels, maybe even more. And that became the second great oxidation event, or, since geologists like multisyllabic words, the Neoproterozoic oxygenation event. And not sure why, nitrogen-fixing bacteria evolved, maybe. Breakup of the supercontinent Rodinia, rock weathering, flood of nutrients. Whatever happened, photosynthesizers went wild, and they turned so much atmospheric carbon dioxide into biomass that then sank to the ocean floor that Earth's greenhouse weakened again, and here we are again, Snowball Earth number 2. If anything, it was worse than the first one. We're now into early November of our cosmic year. At least 2 major events, the ice may have extended all the way down to the equator. There are geologic signatures of this all over. We know much more about this because it's more recent. But eventually it melted again, geologic activity, volcanoes, and a few million years after the snowball melted, maybe because of all that fresh new oxygen, some eukaryotes took their symbiosis cooperation thing to a whole new level. And they started to form multicellular creatures. If ET had checked out the seafloor then, he would have seen something like this. This is called the Ediacaran biota. That's because they were first discovered in the Ediacara Hills in Australia. Took decades to figure out, the biologists to recognize what it was. The thing is, biologists are still scratching their heads. What are these things? They look like seaweed, but if you look closely, and the devil's in the details, they aren't seaweed, like no existing seaweed. They're like no existing animals. They're not no existing fungi. None of them had skeletons or shells or fins or eyes or mouths. None of them, everything we associate with animals. There's no evidence that they burrowed into the sea floor, which was mud. No obvious way to move. So far as we can tell, these things were just sacks of protoplasm. They must have been doing something right because they were around for 35 million years. But we don't know what they were. But 35 million years is just a few days of our cosmic year, remember? And so eventually Earth just said, the heck with it. These guys aren't working. We don't know why. We don't know where they came from. We don't know what happened to them. But about 539 million years ago, they basically just died out. And for a very short while, the seafloor was virtually empty. In fairness, there were a few things that are ancestors to modern sponges and jellyfish, but nothing very advanced. And then suddenly, well, over tens of millions of years, the seafloor exploded with new life. This is what's called the Cambrian explosion. And VT would have had plenty to keep him busy. Not only were these, we have fossils all over the place on these things. Not only were they complex and multicellular, but most of them were related to the ones we know today, unlike the Ediacarans. True, some of them are really weird. You can hear it in the name. That's called hallucigenia. This is called Anomalocaris, for anomalies. Possibly the weirdest of all is that. It's Opobenia, and that's not a weird name, but the geologist who found it, and first found it in 1911, didn't know what the heck this was, so he just named it for a nearby mountain range. But they're all arthropods. They're the same family as shrimp, crabs, insects, and spiders. So are these familiar-looking creatures who showed up at about this time. There were non-arthropods too, and here's one that we might be interested in. It's called Pikaia. It's about 1.5 inches long. And you call it a worm, except that, well, it's got all these muscles here. There's this flexible cord running along its back. Probably not Pikaia itself, but something very much like it was our ancestor. This gave rise to the chordates, the animals with backbones and spinal cords. We don't know why there was such an explosion of life at this time, but one big factor had to be the emergence of predators, animals that eat creatures that eat other things. And suddenly it was urgent to have eyes and legs and flippers and shells and armor and all the ways to defend yourself. It's an evolutionary arms race that continues to this day. Now, this is an extremely awkward place to stop, and I hate doing it because the story is just getting good. And ET is getting really busy. But I've gone on way too long already. Aaron's getting very antsy. And well, this is part of another story, and I'm going to tell some of that in my next talk, if you let me back, which I call the backyard dinosaurs. So for now, let's just look at a few lessons from an alien Earth. One is that the Earth was a home for life out of luck. Our planet was the right size. It could let the hydrogen and helium go, otherwise we would have become Jupiter. But it was big enough to hold on to the heavier gases, carbon dioxide and all the rest. Otherwise it would have become a barren rock like the Moon or Mercury. We orbited in the sun's habitable zone, the right distance from the sun, which means that the oceans didn't boil like they did on Venus, they didn't freeze like they did on Mars, but could stay liquid. We've had liquid oceans, aside from Snowball Earth events, for 4 billion years. And that's something of a miracle. And we also had plate tectonics. We didn't talk much about this, but all that fresh rock coming helps control the level of carbon dioxide and control the greenhouse. So that's actually pretty critical. Second, our world survived some very narrow escapes. Notably, the Snowball Earth didn't freeze as solid, which it easily could have, which would have made photosynthesis impossible, and life would have been trapped down at the deep sea vents. There's an element of reassurance in this story. Earth and life have endured through disasters far worse than anything we could do to it. But that's also a note of caution, because life did recover from planetary disasters and went on to thrive, but only after unimaginable carnage and tens of millions of years of evolution, so that whole new species could arise and replace what got lost. And maybe there's a bit of humility. This fertile oasis that we live on, that geology and life and time have given us, is actually rare and precious in the universe. And it's also temporary, so maybe we can still learn to appreciate it as such.